Hi, in this video, I will be presenting our toolchain PNPEq, verification of scheduled conditional behavior in embedded software using Petri Nets. Um, the authors are myself, Rakshit Mittal, Dominic Blois, and Soumyati Bandyopadhyay. This paper is a collaboration of three institutes, Telecom Paris in France, BITS Goa in India, and Hasso-Plattner Institute in Germany. So, any source program will undergo certain optimizing translations through a compiler, and it will be transformed or translated into a translated program. The question is, do the source and the translated program have similar behavior or equivalent behavior? Are there any bugs in the translated program? So these questions are solved by a mechanism called equivalence checking. And these optimizing transformations can be performed. There are various kinds of optimizing transformations performed by compilers. There is duplicating down, which is basically code moving from basic block 0 to basic block 1 and 2, which are blocks of two conditional branches. Then there is duplicating up, which is code moving from basic block 3 to basic block 1 and basic block 2, where basic block 3 is a merging basic block between basic block 1 and basic block 2. Similarly, we have boosting up where code moves from BB1 and BB2 to back to BB0, and boosting down where code moves from BB1 and BB2 to BB3. And you have useful moves where code can move across the conditional branches. It can move from BB0 to BB3 or BB3 to BB0. So these compiler translations have been described in Bacon et al. In compiler transformations for high performance computing, published in the ACM Computing Survey in 1994. Equivalence checking. Equivalence checking. So biosimulation based methods were the first equivalence checking mechanism proposed by Amir Noeli in 1998. They were enhanced over the years by Nicolas Renard and finally Kundu et al. In CAP 2008. Um, Another class of equivalence checking mechanisms is the inductive inferencing based methods proposed by Matthias in 2014. Um, a limitation of inductive inferencing based methods is that they can only handle scalar handling problems. So they essentially cannot deal with arrays. And a disadvantage of biosimulation based methods and inductive inferencing based methods is that termination is not guaranteed. So termination, which is of course a desirable quality of any equivalence checking mechanism or any algorithm in general, um, is not guaranteed for biosimulation based methods and inductive inferencing based methods because of the presence of loops and possible branches. So to deal with this, path-based methods were used, graph path-based methods. So a control and data flow graph path-based methods were proposed by Karfa et al. To verify the transformations of the Spark compiler, and in 2012. And in the Spark compiler, the control structure of the program was altered, and their CDFG path-based methods was able to verify such translations. This this path-based method was further enhanced and modified by Banerjee et al. Using the value propagation-based method, and by Choksi et al. In 2019 using an extended value propagation-based method. A limitation of CDFG path-based methods is that they cannot they cannot represent parallelism, and so they cannot deal with parallel programs very efficiently. In which case, Petri Nets are chosen as an apt model where they can also represent parallelism. So Samatulyata was proposed in 2017 as a Petri Net pass-based equivalence checking mechanism, but it had a huge model size. The model size was reduced in 2020 in Samatulyata too, but um, the model size was further reduced in our recent paper published this year in 2021, where the model proposed will also be used in our current toolchain, which is PNPEq. A limitation of our previous paper is that um, path explosion occurs in the case of conditional optimizations, which is not desirable and which makes the equivalence checking mechanism slow. So, to deal with that, we have devised a new equivalence checking mechanism, which is the basis of this paper. Coming back to our question, uh, so how to verify these translations effectively? Because equivalence checking is a tedious task. So for us, we use Petri Nets. In PNPEq, we use um, the Petri Net model proposed in our previous paper, where the source and the translated program are constructed or represented by the respective Petri Nets, and then we check for equivalence between these two Petri Nets to verify equivalence between the source and the translated program. So, and that is what PNPEq stands for, which is Petri Net Program Equivalence, which is our toolchain. So the toolchain is something like this. The source program and the translated program undergo are fed into a model constructor block which returns a Petri Net model N0 and a Petri Net model N1 corresponding to the source program and the translated program. Paths are extracted or path covers are deduced from these two Petri Net models. The respective path covers are deduced. Path covers are the list or sequence of all paths in the Petri Net. And then finally, we check for equivalence between these paths. The equivalence checking principle will be described shortly. This is done through a path-based equivalence checker block, where a path analyzer generates input expressions for the Z3 theorem prover, which is also a part of the toolchain. An SMT solver brings robust, verifiable SAT solving, SAT problem solving mechanisms. And so we have integrated an industry standard SAT solver, SMT solver too. Um, so paths, so since we are talking about, since Petri nets are graphs, we use the notion of cut points to unroll loops, which makes graph-based methods terminable, which guarantees termination. And so we construct finite paths from this graph-based methods. Paths are constructed from cut point to cut point, where cut points are nodes, which are either inports, outports, places with back edges, or bifurcation points. All of this is described in the paper, and due to limitation of time, I won't be able to describe it in detail. So the example source PetriNet, the example source program which we have taken looks something like this, where using the available resources, the source PetriNet uses 6 cycles to execute the entire program, and this is the corresponding PetriNet for it. This is actually one single PetriNet, but due to limitation of space, I had to divide it into two. This is place 5 and this is also place 5, and the translated program basically introduces parallelization as well as conditional optimization, so which reduces the entire algorithm to just 2 cycles using parallel threads. So this is the corresponding Petri net. So the paths in the source Petri net go from alpha 1 all the way to alpha 13. The paths in the translated Petri net go all the way from beta 1 to beta 18. So that is essentially the path cover which is generated from the path extraction module, the path constructor module. And so the path constructor, so the equivalence checking principle is based on concatenation of paths. So paths can be concatenated. Path concatenation can be achieved in two ways: path extension and path merging. And so paths can be extended and merged based on certain preconditions, and the results will differ accordingly. The equivalence checking principle goes something like this. For all paths in N1, if there exists a path in N0 such that the paths are equivalent and vice versa, implies Petri Net N0 is equivalent to Petri Net N1. And of course, two paths are equivalent if the condition of execution and the data transformation function for both of these paths matches. So, with respect to the example which we have taken in our paper, the corresponding equivalent paths are displayed in this block on the right. Beta 1 is equivalent to alpha 1. Similarly, beta 2 is also equivalent to alpha 1. Path extensions and mergings also take place in our taken example in our chosen example. I would like to assert, corresponding to the example which we have taken in our paper, that in this box here, so all betas, like which is basically all paths from the translated program beta 1 to beta 18, um, have an equivalent or consist or correspond to an equivalent path in the translated program. Similarly, all paths from the path cover of the source program, which is alpha 1 all the way to alpha 13, um, have an equivalent path in the translated program, which is all the betas. So this is how equivalence between the true Petri nets, which is the source Petri net and the translated Petri net, is verified. And all of this is also described in the paper, so you can go through it. We carry out a validation of our tool chain using a benchmark, uh, where we are comparing our toolchain PNPEq with the FSMD, which is the CDFG extended value propagation based method, which is described in the state of the art, and PNPBEC, which is our previous which is our previous paper. So we check the capabilities for different for these different tool chains, and we compare them for parallel and sequential programs. So some limits and capabilities of our toolchain is that we cannot validate array handling programs yet. Software pipelining transformations also cannot be handled. Loop reversal transformations and invariant assertions based transformations also cannot be handled by our toolchain currently. But we can validate uniform and non-uniform code transformations, loop swapping transformations, thread level parallelization transformations for scalar handling programs. So I hope this presentation has been informative to you. Please go through our paper, and if you have any questions, you can direct them to either me, Dominic, or Samyadeep. These are our email IDs. Thank you for this opportunity, AppSec, and hope you have a nice day.